Hello everyone, welcome back to another video. In today's video, I have yet another challenging integral in front of you. And this integral is actually pretty challenging. Now, when you look at it at first, you're like, oh, it looks easy. It's just one function. It's a 20-second integral. But every supposed easy integral requires a first step. And what do you think is the first step to solve this particular function? Well, you can use integration by parts. You can use partial fractions. You can even use u sub. But to do all of that, you need more than one function. There's many other fancy ways as well. But over here, we just have one function. And to make things worse, there's a root over there. So it's a pain in the ass. Integral of root of tangent x. So we have to start somewhere. Let's directly start with substitution, right? Now, there's two things I can do. Either I can substitute the entire function as u, or I can just substitute tangent x as u. In my opinion, I should take the whole function as u, because then whatever dx is remaining, based on what I take, I'll take its derivative, I'll square both sides, and then I can isolate dx. So then we can change dx, but the function in itself, that has to be taken as u. So I don't want to take root of u or whatever, so I'll just take the whole thing as u. Let's start with substitution. Let's put root of tangent x. Root of tangent x is u. So now we have to find du, but we have root of tangent x as our function. Now if I say, okay, find the derivative of tangent x, you'll directly say secant square x. So instead of doing du, let's do 2u du, right? Because let's also find the derivative of this. So find the derivative of this by squaring this. So this becomes u squared, which is equal to tangent x. And now, just like I said, 2u du, because we have finding the derivative of both sides. So it becomes 2u du equates to secant square x with respect to x again. And there you have it. As I told you, now you need to isolate dx, because that's another familiar face in our integration problem. So let's isolate dx. Dx is equal to 2u du divided by secant square x, right? And now we can substitute things into our integral. This becomes the integral of what? We've taken the entire function. That's why I've taken the entire function directly as u. Because if I would have taken tangent x as u, then it would have been root of u and all that, more pain. So to the power of half and all that. Instead of doing all that, just take the whole function as u, finish it off when you don't understand what to do. So then this just becomes u times dx is what we have changed to 2u du divided by secant square x. And now we're stuck, as you can see. But you know what I always say, whenever you're stuck in an integration problem and you have 2-3 functions and one of them is an odd one out, just take a look at that function. If you look at secant square x carefully, see, if you look at this entire function, over here u is in terms of u, 2u again is in terms of u, and this whole integral is in terms of u. And over here, when extra fit, we have this secant square x, right? So secant square x is like the odd one out. So we have to find some way to represent secant square x in terms of u to make this easier to integrate. How are we going to do that? Using a general identity, which I'm pretty sure everyone would know. 1 plus tangent square x is equal to secant square x. This is none other than the Pythagorean identity you would have learned in class 9 itself. Class 9, I think CBSE people in class 10. Secant square x. Basically 1 plus tangent square x. This identity is very important for what we are going to be performing right here. So just pay attention. So if I just substitute 1 plus tangent square x instead of secant square x, 2u du divided by 1 plus tangent square x. Just a few moments ago, I had said that tangent x is equal to u squared. So then if I have to further square this, I have to square this as well. So if I square both sides, it's going to be u squared whole square, which is u to the power of 2 into 2, u to the power of 4. Is it not? So this integral just becomes u times 2u du, and it becomes 1 plus tangent square x is just u squared whole squared. So it's basically u to the power of 4. So we can say u to the power of 4 plus 1. Again, this u can multiply over here. So we can rewrite it as 2u squared over u to the 4th plus 1 with respect to u. And now, as you can see, we have completely rebranded our integral. It started as root of tangent x, and now it has changed to this wonderful expression over here. This is still a pretty tricky integral now. You can't directly solve it. See, if this u to the power of 4 plus 1 was in the numerator, we could have separated it into 2 different integrals, cancelled off the u squared, done whatever we had to do. But over here, now we can't, because in the denominator, we have 2 different terms. So we need to find some way to kind of, we can't use substitution, obviously, directly over here, because this is something else, this is something else. If you take iska derivative, there's no way of substituting that into this. Similarly, this derivative doesn't match the numerator in any way. From what you guys can see, you can't just directly, use substitution over here. And I think I know the reason why, because it's u to the power of 4. Like, it's a really high degree. Why would you want to complicate your life by keeping such a high degree present over here? So how about we just get rid of that, or try to, lower the degree? That would be a pretty good strategy. So to do that, I need to let's make this u squared, which we can, right? By dividing this by u square, it's going to be u to the power of 4 minus 2. But how do we do that? Anytime we need to make any change in the numerator, same thing has to be made in the denominator, vice versa. So what I'm going to do is I'm going to basically divide by u squared. So multiplied by 1 over u squared. I'm going to do that throughout. U to the 4th multiplied by 1 over u squared plus 1 over u squared. Because it's basically 1 into 1 over u squared. Du. But what do we need to do? This cancels off with this. This cancels off with this twice. So it's integral of It's just 2 in the numerator now. We just have one constant in the numerator, that is 2 du. And now this is what? U squared, right? This is just u squared plus 1 over u squared. All right, so now we formed a brand new function. This function has been formed in itself with a lot of algebraic manipulation. But to continue this integral, we need to perform even more, algebraic manipulation over here. So after this, what do? Again, we are stuck. Just think about it. Okay, in the denominator, we have u squared plus 1 over u squared. Numerator, we have 2. We need to find some way to connect the numerator and the denominator. Of course, again, what are we finding the derivative of, right? Think about that. But we can't directly find the derivative of u squared plus 1 over u squared. But there's one thing, I don't know if you guys noticed, but isn't this a perfect square? Isn't this a perfect square, right? Because it's u plus 1 over u whole squared, so it is a perfect square. So whenever I say the word perfect square, what's the first identity that comes to your mind? A plus b whole square, isn't it? So to explain what I'm going to do here, I'm going to do a little rearranging. This is basically just a square plus b square, right? So it's going to be a plus b whole square minus 2ab, or plus a minus b whole square plus 2ab. To do that, I'll actually do some substitution over here. Let's say u squared is equal to a squared, and 1 over u squared is equal to, let me say it's b squared. So now we perform the identities. A plus b whole square, let's start with that, is equal to a square plus 2ab plus b square. So can't you see this a square plus b square, which is exactly what is in our denominator over here? So we want to sort of, isolate that. How would we isolate that? Basically, take the 2ab to that side. A square plus b squared, if you want to isolate, is just going to be equal to a plus b whole square minus 2ab. And now we had taken what? We had taken u as a and 1 over u as b. So substitute that in now. U squared plus 1 over u squared. This equates to what ultimately? This equates to u plus 1 over u whole square minus 2. Because u into 1 over u, it's 2ab basically. A is u, b is 1 over u. U into 1 over u, u's cancel off. So it's just minus 2. This is the first way we can express it. It's just the first way. Let me tell you, there's yet another way we can express it. Okay, so this is the first way. The second way we can express it is in terms of a minus b whole square. If we do this, we'll get something similar, a square plus b square. But this time we get minus 2ab. But this though is intact, right? This is what we want, a square plus b square. We want to isolate this. As long as that is there, khel khatam. So now minus 2ab. And now this is just going to be a square plus b square is equal to a minus b whole squared plus 2ab. Send the minus 2ab to that side plus 2ab. And now do your general substitution in u squared plus 1 over u squared. What is this going to be? This equates to u plus 1 over u. Sorry, u minus 1 over u, right? U minus 1 over u whole squared plus 2. So basically now we have found two ways to rewrite it. We've not done much. In fact, I already anticipated. I told you that it was a perfect square. But I just showed you how we can rewrite it, right? All this is really not necessary. However, now that we've gotten this, we've gotten where it comes from, basically. U plus 1 over, we found a new way to replace this, at least. We found a new way to replace this. But what do we use and why do we use it? We need to take something that is going to be profitable towards our integral. I have designed some red boxes, and I'll tell you exactly why I have decided to make these red boxes, because we are doing yet another substitution. And this one is probably going to be the last substitution we'll do here. After this is just direct integrating. Yeah, actually no, there's probably one more substitution coming ahead. But what am I going to substitute? See, ultimately, why are we doing all this? To maintain relations between the numerator and the denominator, isn't it? That's what we are here to do. Now, numerator is very simple. It's just a constant 2. But what about the denominator? We need to find some way to do that. How do we do that? Function and derivative. Always remember that works. Function, try to connect it with the derivative. Over here, we can't directly find this derivative. So we'll have to find the derivative of this. U plus 1 over u. And we have to find u minus 1 over u. So let's do that. Let's take t as u plus 1 over u. We'll take that as t, right? And then we'll take another variable k, u minus 1 over u. So we've done some substitution over here. So now find the derivative of it, dt. dt will be equal to what? U is just 1 because it's with respect to u. 1 plus 1 over u will be 1 over u whole square, but negative of that. So here will be 1 minus 1 over u squared, right? And this one will be u minus 1 over u, so it will be minus of minus 1 over u squared. So 1 plus u, 1 over u squared. Yeah, that's pretty much it. dk will be this. All right, so now we have, okay, I don't know if you noticed this as well, but if you add dt and dk, what do you get? 1 plus 1 over u squared plus 1 minus 1 over u squared. Negative 1 over u squared cancels off with positive 1 over u squared. But then we have 1 and then another 1 over here. 1 plus 1 is 2, which is exactly what we have in our numerator. Okay, so we finally found a way to connect it. Let's go. First thing we've completed is finding some connection. So now how about you replace 2 in general with this? So it's just going to be integral of 1 plus 1 over u will take for now. 1 plus 1 over u squared plus 1 minus 1 over u squared with respect to u right now. And then we'll take the same thing, u squared plus 1 over u squared. Denominator remains the same for now. Now I know that I had expressed two ways to rewrite it, but this is separated by a positive sign. So we can separate it into two integrals. And based on what satisfies, we will use that method of expression. Are you getting what I'm saying? So split it into two integrals. First integral will be 1 plus 1 over u squared divided by, now this we have to find which way to express, right? Which way should we use to express u squared plus 1 over u squared? Now for that we need to look at this. How did we get 1 plus 1 over u squared? By differentiating what? U minus 1 over u, which is present within which function? This function. So which method will be used to rewrite it? U minus 1 over u whole square. So u minus 1 over u whole squared plus 2. This is how we're going to rewrite this particular function. Plus, it's plus only, right? Plus integral of, this thing will be 1 minus 1 over u squared. So 1 minus 1 over u squared divided by, now we need to use the other way of expressing it because we've already used this, right? And how did we obtain the derivative? How did we obtain 1? How did we obtain this? How did we obtain 1 minus u squared, 1 over u squared, right? We obtained it from this because we had substituted k as u minus 1 over u. So this thing is u plus 1 over u whole squared minus 2. So it's just u plus 1 over u whole squared minus 2. And there you have it. Two new ways of representing this. All right, so that's pretty much it. So this is our new integral now. I'll box it so that I can show you exactly what it is. So integral of 1 plus 1 over u squared divided by u minus 1 over u whole squared plus 2 plus integral of 1 minus 1 over u squared divided by u squared plus 1 over u whole squared minus 2. To read it only, it's so much. So now we just need to figure out what we had substituted. That's why I made these red boxes. Okay. So see, we had taken t as u plus 1 over u. U plus 1 over u. Okay, we'll deal with that later. We'll first deal with this. U minus 1 over u we had taken as k. Right? So the denominator will be dk basically. Integral of dk. Integral of dk over, this is what? K square plus 2 ultimately. K square plus 2 plus integral of what? This thing will be dt, right? dt over t squared minus 2. And that's pretty much it. That's pretty much it. This is all we needed to do. So now we've gotten a brand new expression and we have to further integrate it. But doesn't this look a lot less challenging than whatever we had previously done? Right? We kind of simplified it. Now, henceforth, we have to use a little bit of, I would say, advanced concepts. In this, we'd have to use hyperbolic functions and other ways. You can also use partial fractions to integrate this. But I would like to use hyperbolic functions. I would say that's easy. Because whenever you have something in this form, see, I don't know much about hyperbolic functions, but they basically define it using hyperbolas rather than circles or the unit circle in itself. So yes, in this form, since it's subtraction over here, we will use hyperbolic tangent, right? And over here, this is positive. So we'll use tangent. Wherever it's positive, we use tangent. Wherever it's negative, we use hyperbolic tangent. Got it? So I think on that note, let's deal with it now. So how do we use the hyperbolic tangent? We need to make, again, a substitution, obviously. So to actually make that substitution and carry it out, I need to factorize something. The only constant over here we have is 2. So let's factor out 2. Let's factor out 2. How do we ultimately factor out something? We just divide each and every term. So we divide the numerator also by 2. And in the numerator, we have 2. That's the constant. We integrate it out. So it's just half of integral of dk over k square, right? K square over 2. K square divided by 2. But this, again, we can take k over 2 whole square. So k over root 2 ka square, we can take it as k over root 2 whole squared minus 1, because 2 divided by 2 is just 1. This is the first thing we can write, plus, again, half. We do the same thing but with t instead. So half dt over t root 2 ka whole squared minus 1. Now, why am I actually doing this? This might actually confuse a few of you why it's t over root 2 ka whole squared, because this thing was already t squared. But then since we are dividing by 2 again, I'm opening a bracket, making it t over 2 ka whole squared, root 2. So it becomes. So if we have to find the square root of 2, which is root 2, we'll just open the bracket. It'll be this thing whole of square. All right. So now we've got this. Now I think it's a good time to use our hyperbolic functions. So let's dive into it. As I said, hyperbolic tangent is what we need to use. So let hyperbolic tangent. As I told you, for this we'll use hyperbolic tangent. For this we'll just use tangent, right? Let hyperbolic tangent theta equate to t over root 2. So basically we can say that t in this case would be root 2 hyperbolic tangent theta. So what is going to be the derivative of t? What is the derivative of tangent? Secant. Hyperbolic secant in this case. So root 2 secant, but it's secant square, my bad. Secant square is basically the same, but they just use something else to define themselves. So secant square, my bad. Secant square theta. And yeah, we are taken t as root 2 tangent, and we are taken hyperbolic tangent theta as t root 2. Now this is t root 2 whole square minus 1. So isn't it this squared minus 1? Hyperbolic tangent square minus 1, right? This thing, the denominator is hyperbolic tangent square theta. If we have to find its derivative, again, it will be secant. So denominator though will just be secant, negative secant in this case. So it will be negative secant, hyperbolic secant square theta. That's going to be in the denominator again. We have to find its derivative also, right? And now just replace it in this. So over here we have root 2 hyperbolic secant square theta divided by negative of hyperbolic secant square theta. And now this changes also because we have used theta. So it changes, becomes with respect to theta in this. So this cancels off with this, as you can see. So now we are just left with negative root 2 theta. But then again, what's theta ultimately? We have to rearrange and find theta. What's theta? We had said that hyperbolic tangent theta is equal to, we had taken as t over root 2, right? T over root 2. So if you want to get theta in itself, we have to take the inverse hyperbolic tangent, as you may be knowing. So inverse hyperbolic tangent t over root 2 is what will be taken. This is theta. But this is not really what we are going to be needing. We'll do this later. We can also do these substitutions later. See, we are almost done with our sum. Okay, so tell you that. But I just want to, tell you the concept. Basically, this is what we'll be applying over here. And the same thing we'll be doing over there. But over here, we'll be using tangent. Over here, we are using hyperbolic tangent. And plus over there, the sign though will change. So ultimately, it is what? It is the integral of what? We've integrated it now. Making it, sorry, this is not integral of this. We've integrated it, making it negative root 2 theta, right? And then we've also gotten theta as this. So we have basically gotten our answer. This part of the integral is set, but that part of the integral, again, instead of tangent, it's hyperbolic tangent. So we also change theta. Instead of theta, I'll use phi. Okay, I'll use phi to identify that. And that's pretty much it. This is integrated like this. Okay, we basically just integrated it now. And it's pretty much done. It's integrated. We don't even have to integrate the other function because it's the same thing, right? The same concepts will be applying over here. Same substitution will be carrying out. But over there, the sign though will change. It won't be negative root 2 theta, but it'll be root 2 theta over there also. But it won't be theta again since we're taking tangent instead of hyperbolic tangent. So half though will be there. Hyperbolic tangent, this I'm establishing. This we have established, right, to be in that function. So now half though is there in both. Half though is there in both. The first thing will be positive root 2 theta. Positive root 2, sorry, not theta, phi r. Positive root 2 phi. And then it will be plus minus root 2 theta. But plus minus is minus only, so minus root 2 theta. Done. Integration is all done. We've done it. Using the hyperbolic functions, this is the advantage. You don't even have to actually go integrate each and every term because it gets integrated. It's a function in itself. So because we have established that, we have to take its derivative, all that we have done. Integration is done now. Now we just need to figure out the values of phi and theta, and we're sorted. I already showed you what theta is, by the way, which is hyperbolic tangent inverse of t over root 2. I already showed you this, right? So this thing is done. This thing is already dealt with. Oh, root 2 though is common. Can't we factorize that out? Root 2 over 2 it will become, which is again 1 over root 2. Because root 2 goes into root 2 times. So 1 over root 2 it becomes phi minus theta. All right. So this again, now we have to sit and solve it patiently. See, you know that theta, I'll write it again. Theta is equal to hyperbolic tangent inverse of t over root 2. So that will be k over root 2. But it won't be hyperbolic tangent. Phi in this case will be equal to tangent inverse of k over root 2. All right, that's pretty much it. We're done with our integral. Integration though is done now. Now we need to substitute our values in. Basically, it becomes 1 over root 2. 1 over root 2. Phi minus theta we have. Phi we've gotten as tan inverse k over root 2. Half of tan inverse k over root 2 minus hyperbolic tangent. And this will be what? T over root 2. T over root 2. Pretty much dealt with over here. All right. And now all we need to do is substitute our values in and then we're done. And then 1 plus c constant of integration though is there. Don't forget that. Okay. So now we have basically finished our integral. Now what do we need to do? We need to figure out what is k, what is t, all that. K was what now? This is why I was marking everything. K is u minus 1 over u. U, remember, is what? Root of tan x. So root of tan x minus 1 over root of tan x is just k. So tan inverse root of tangent x minus 1 over root of tangent x divided by root 2. This is just the first part, by the way. Minus hyperbolic tangent inverse root of tangent x plus 1 over root of tangent x again. Root of tangent x divided by root 2 plus the constant of integration. And that's pretty much it. We're done. This is our answer. Doesn't this look beautiful, what we solved over here today? This small little function has gone through so much and finally taken its form this. So using hyperbolic functions means less work. Partial fractions also is a method that's possible, but over there we actually need to sit and integrate. Over here you don't even feel like you're integrating. It was just transformation. This transforms into that. Transformation and substitution. But the amount of concepts that we used in this really will help you, improve your integration skills. So if you want to get better at calculus, you need to keep performing problems like this that require lots of algebraic manipulation, changes, all that. So this is quite a challenging integral, definitely challenging. Took me like 3-4 tries to actually get it properly, but this was my solution. I hope that you enjoyed this video.